Gonna get started here soon. Gonna grab a link for the Discord. Alright, we are live. The link is in Discord. See who all is going to log in today. I'm guessing most of you watching this are probably watching this after your clinicals today, hopefully. Hello? All right, awesome. So I'm hoping you guys all got a chance to watch through the content already, gone through the lecture material. Watching me while cleaning house. Nothing wrong with that. A little bit of multitasking. All right, so the plan I had for today was, we've been finishing going through deep cleaning the last few weeks too. Our house is a disaster after this corona situation. We got it under control now though, I think. But anyway, today we're going to go over some practice problems for dienes, and then I also want to do some aromatic problems, and that's pretty much all I had planned for today. I didn't want to go into any new content because we have the exam coming, so basically just practice, that kind of thing is what we're going to work on. So while I have a few of you guys here, I did want to talk a little bit about lab and the changes I'm going to make. I'm pretty sure you guys are all going to be okay with this change. All right, so normally I would have this week's lab to go over. I'm still going to go ahead and give you guys the handouts for lab. And we only have 2 labs left, I believe. 2 labs left. And what I'm going to do is, so the reason why I didn't want to get the lab this week today was because the content of the lab is actually next week lecture. Because I didn't feel that we were ready for the aromatic reactions yet, which is what that lab is all about. It's all about the electrophilic aromatic substitution, which I'm going to go over early next week. And I figured we can just push off that lab. And due to the nature of the way we're doing the labs, I'm thinking that what I'm going to do for the last 2 labs is just drop the assignments completely, and then go ahead and just roll some questions into the final. So the coming exam and the final. Sorry, that's the homework too. What do you mean? I wasn't sure what you were responding to. Anyway, what my plan was to go ahead and to so I'll mention that during the worksheet too. The homework this week, only 1 page we got to, and I'm actually going to do the whole page in the stream today. So, and remember, I don't collect the worksheet the week of the exam because I want you guys focusing on the exam instead. The homework is meant to do. You do it. Don't just practice, get it out of the way, but don't worry about submitting it. So anyway, there's not going to be any more written assignments for the next 2 labs, but the stuff from the labs are going to be on the final, and as well as the coming exam. So you still have to study them. So we do have one. So they won't be on this coming exam, but I'm thinking like the exam 3, and then the final are going to have lab questions on there about the 2 labs that we're kind of skipping. So make sure you read them. And I think what I'll also do is I'll also still get videos for you. I'll basically just provide everything I normally would, just without the assignment. So you'll have the handouts, you'll have the videos, all that fun stuff to study from. And I really think I have to provide the videos because you kind of need to see some of the stuff to understand it, I think. I feel anyway, that you need to kind of see things. With that in mind, did you guys have any questions about anything before we get started today? And now I'll get a drink of water while you get a chance to ask a question. Someone is typing. So the question was about exam 2 being opened. So I was planning on working on that. I was going to get it started today, and then the conversion process to making a canvas is going to happen tomorrow, very likely. But yeah, tomorrow I made someone a promise in the Discord that I'll have up by tomorrow, and that's what will happen. There are no worksheets due the week of the exam. So this week is an exam. That worksheet is not due. So that's just meant for extra practice. So I am, however, going to be rolling that particular worksheet into next week. So if you've started on it already, then you are perfectly fine. Yeah. All right. So let's go ahead. Without much further ado, I wanted to go ahead and work on some dying problems. Hopefully you're not dying over this. Sorry about all the puns. I think I might just push both to Sunday. Yeah, I think I'll just go ahead and push both to Sunday. Give you guys extra time to work on it. That's fine. I'm becoming more relaxed as this situation goes on. I don't like teaching online. I don't like doing organic online. I like doing in person. Yeah, I'm becoming more and more relaxed as the weeks go by. Ugh. I know you guys are enjoying that, but yeah, it's not my style. All right, so here we go. Oh, and I did fix the focus. There was a focusing issue. I didn't realize it. I went back and watched the streams, and I realized that the dot cam was kind of blurry on some of them. And I think I fixed the focusing issue now, so this should be pretty good, crisp detail. I'm seeing it very clearly on my screen. So I want to go ahead and have a reaction with HBr. All right. So in a dying problem like this, there's two things you need to consider. Well, the main one is which double bond is going to react. Yeah, that's probably your internet. I'm sorry, but yeah, it's very clear on my end, and I'm streaming at 1080p and 60 FPS. So I can't go any higher. My video card will not let me broadcast in 4K. So. Yeah, I would need to upgrade my video card for that. Anyway, you need to think about which double bond is going to react. You also need to think about where the plus charge is going to go. So typically the plus charge is you want it allylic to the other double bond. That'll be one of the most stable carbocations. So what you need to do is think about, okay, is this one going to react? Is this one going to react? And then is the plus charge going to go here or here? And I'm going to go ahead and mark the most stable carbocation position would have been here, assuming this one reacts. So let's go ahead and just do the mechanism for the first one, and then we'll just do, all right, so acid base, protonation. So we end up with this. This one already had an H. The new H is here. This is the new H, like so. Plus charge is now here, and like so. All right. Typically, if you're being asked to show the whole mechanism for this, typically what I'll do is I'll ask you guys to show me both products possible. And in order to get to that, you have to show the resonance. So I'm going to go ahead and show resonance. So like that. The resonance that we're doing here should be a lot more simple than what we saw earlier in the semester. That stuff is actually a lot more challenging than what we do later on, honestly, in this course. Yeah, most of the resonance we're doing here is just like one bond moving, and then next, the aromatic stuff we have 3 arrows moving, but it's honestly not that bad. The stuff we were doing earlier I thought was much harder than this stuff. All right. So after we have the 2 carbocations, I am seeing this one is more stable. We did, if you went over the notes, you should have saw that there was the consideration of kinetic versus thermodynamic. It works out where this carbocation is more favored thermodynamically because it's more substituted. So let me write that in here. This is more substituted, therefore more stable. And then it's just less for both on these. So less substituted, less stable as a result. So what ends up happening is that this one is actually easier to make. This one has a higher energy of activation. So this one's going to lead to what we call the kinetic product. Because intermediate is easier to make, it can get to this easier than this one. So this one forms faster. The main difference, though, is your actual product. Like that. So we have the 1,2 product versus the 1,4 product. So let me go ahead and draw and make sure I'm highlighting the H's here so we can clearly see why we call them 1,2. So that's the 1,2 product. And then the double bond now here, and then that. I do want to point out the H is in the same spot still. It's still at 1, so that's the 1 in both of these. The 1 is the hydrogen, the 2 or the 4 is the bromine. And I also do want to point out that these would both be racemic because of the fact that we have a carbocation mechanism. These are arguably racemic. So once again, we had 1,2 versus 1,4. So this one is forms faster, but it's less stable. And then this one is more stable. And this is basically in reference to the double bond. So if you think about it, here we saw earlier during the elimination chapter that the more substituted the alkene is, the more stable it is. So here we have a disubstituted alkene versus a tri-substituted alkene. This one's more stable thermodynamically. All right. So once again here, this one forms faster because the intermediate is more stable, but the end product is less stable. And then the flip everything on for the 1,4. So for this one, the intermediate is less stable, therefore needing a higher energy of activation to get to it. But the end product is more stable. So I'm not going to do the graph here, but you guys should have gone and looked over the graph of this. It basically puts everything I'm saying into graph form. So make sure you study that for the exam. All right, let's go ahead and do one more of these. I want to change it up just a little bit. Something else we haven't really talked about, and that's deuterium tagging that people do sometimes. So I'm going to go ahead and double bond here like that. And then what I'm going to react this with is DBr. You should have covered deuterium atoms during your freshman chemistry classes, typically the second semester. Deuterium is an isotope of hydrogen. So basically what D means, it's heavy hydrogen. So I like to call it heavy hydrogen. We call it deuterium for short. Deuterium. So the way that deuterium is utilized in organic chemistry, or one way that they're utilized, is if someone was trying to figure out what this mechanism was, they can run it with this derivative of HBr, but instead of having H there, it has deuterium. So they are different from an isotopic perspective, meaning it's heavier, but from a chemical perspective, they are identical. So this allows chemists to kind of trace where H's are going to go in a mechanism. Because if you think about it, if you have all these H's on there, they don't know which H came from the HBr. So we have to have some way for them to stand out. So this kind of stuff is commonly done with deuteriums, and it's also done with heavy oxygens. Oxygen 18, I remember right. I think oxygen 18. I'll have to look it up. I'm pretty sure it's 18. But yeah, so this stuff is used for tracking mechanisms in some cases. The way you want to approach it is the same, but instead of an H, we have deuterium. This is commonly done in questions I see typically for like multiple choice, and it's a way for a test writer to put a mechanism in a multiple choice question. Because if you don't know the mechanism, you don't know where deuterium is going to go. So you'll have a bunch of choices where deuteriums are in random locations, and you have to pick out the correct location. I'm just going to draw the products here. I'm not doing the mechanism here. I'm just going to do the products here. So 1, 2 would go with deuterium here, with bromine there. That's the 1, 2. So let's do red. It's fine. 1, 2. And then racemic as well, just like the last ones were. And then we have the 1, 4. So when drawing the 1, 4, you want to try to do these without the mechanism. So without the mechanism, we know that this double bond is going to move here. From knowing the mechanism, we know that. And then 1, 2, 3, 4, bromine goes here, like that. And that's the 1, 4 product. And I want to write a few other little comments in here. Do you guys remember, anybody in the Discord remember from studying how we can prefer one over the other in lab? Like, what can we change about our lab setup to favor 1, 2 versus 1, 4, for example? What could we do? So just to clarify, the question was, if I want to specifically get the 1, 2 product, how do I do it in lab? So the question is, which one is favored under high temperatures? Which one's favored under cold temperatures? You remember which one is which? Yeah, 1, 2 is favored in cold. So going back here a little bit, just backing up a little bit. I mentioned earlier that the intermediate was like a deciding factor on the initial activation energy. It turns out that in order to have the energy to favor this one, basically favor this pathway, you have to have more energy, more heat. If you have less heat, it'll favor this pathway. So I want to just add the notes in here of hot versus cold. So for 1, 2, let's go ahead and say it's cold. Low temp. Oftentimes you'll see things like 0 degrees C, minus 77 degrees C. These are 2 common temperatures you see. They're very specific for conditions in lab that are easy to set up, but these are common cold temperatures you see for this reaction. And then for hot, we'll say that's high temperature. And I would say that this one would be like 100 degree plus, so above 100 degrees C. If you see a problem with it where it's telling you room temperature, it's looking for both. So I'm going to add that little comment down here. If you see room temp, show both. Because if you think about it, you're kind of in between, so these are going to be in equilibrium. So just show both for room temp, just to play it safe. And just so you guys know, 0 degrees C, you guys should know that one. That's an ice bath, ice water bath. This one's probably not as common, though. It is common for those that work in the lab a lot, though. This is dry ice and acetone. So if you take dry ice, like the kind you get from Albertsons, the dry ice, and drop it in pure acetone, it'll start spattering really fast at first, but eventually the acetone will cool down, and it'll settle at minus 77 degrees C. Super, super cold. That stuff is fun to work with. Yeah, when you drop the dry ice into it, yeah, I don't know. Dry ice is fun to play with. Speaking of dry ice, Tristan and I filmed some footage for backyard chemistry for you guys. I need to cut it together and post it. But yeah, we did demos in my backyard for you guys for 4th of July. I just haven't made the video together yet. But I have the footage. Gotta put it together. Is there any questions about 1, 2 versus 1, 4? I think we've covered it thoroughly. I want to go over Diels alder next. All right. Okay, go ahead and ask your question. You can answer when we get to it. All right. So All right. So the other reaction you should have gone over is the Diels alder. I'm going to give you the crash course right now. I do have a much more longer video on the channel. The focus today here is to do some problems, but I need to do a little bit of an intro. This is how I do it, how I would do it in lecture anyway. Even after I covered it fully, I would have talked about it again. All right. So typically for a Diels alder, it's a very specific reaction. It just happens to include a conjugated diene. So here we have a conjugated diene. Let's go ahead and let's use purple for notes. So typically you have a conjugated diene. This is typically referred to as the Dienophile. Or sorry, the diene. And then we have another pi bond. I do want to mention here that it could be an alkene or an alkyne here. So alkene or alkyne in this situation. That. All right. The other term we use for these here is because the conjugated diene is electron rich, this is going to be the nucleophile in the mechanism. Nucleophile. We don't use it in the same way as like an SN2 nucleophile because it kind of cyclizes, you know, but the way you want to think about it is the same. And this other one here, we call it the Dienophile. If you haven't learned your prefixes and suffixes on science words yet, the suffix phile means to love or like something. So when it's saying Dienophile, it's saying it likes dienes. It loves dienes, essentially. All right, and it works out in this particular context, the Dienophile is the Electrophile. It's the electron poor species. What's going to happen is between the carbons 1 and 4 are going to connect to this alkene or alkyne, and then the arrows go like this. So you don't have to draw it this way. You could show this bond going straight to the carbon, but I like showing the new bonds, the emphasis on new bonds. So you basically get a cyclic arrow push all at once, concerted all at once. And when starting out here, what I recommend doing is you're always going to get a cyclohexene in your structure somewhere from a Diels alder. So I like to start by drawing the cyclohexene and then adding on any extra parts. So that is the new double bond. Oh wait, I'm going to highlight the new bonds in red. So new bond is there, new pi bond. We also have the sigma bonds here and here that are new, like that. These are single bonds here to make sure you guys are clear. These are single bonds. They are the new single bonds. And let me just make this one a little thicker so they all appear to be the same thickness. Like that. So you get a cyclohexene from this. Once again, the tip I recommend on these problems is because you know the one on the test it's not going to be that simple, right? So you have to draw the cyclohexene and then just tack on the other pieces in the correct location. It's not that difficult. You guys can do it. I believe you. I believe in you. All right. So I'm going to do one. The first one here I think is pretty obvious how this should go. But I want you guys to understand the logic of why I feel that it's obvious. And the key is recognizing which one is which on these two, nucleophile, electrophile. I know a lot of books like to give the new words diene and dienophile, but I want you guys to still keep in your brain it's still these two. Every organic reaction is these two. Electrophile, nucleophile. Only exceptions to that are your radical reactions. Oh, one thing I didn't mention earlier here is that the double bond here needs to be in the S-cis conformation. That means that the double bonds are pointing in the relative same direction. I like to think of it as Pac-Man eating a pellet. So the diene is Pac-Man, and then the dienophile is the pellet, essentially. One thing I show you how much of a video game nerd that I am. All right, so when students do these problems, I recommend that you draw them in the orientation that I do this one in. Like, I will always redraw my structures to be like this, where Pac-Man is pointing towards the right, towards the pellet. And then I'll put it in the orientation so that any bulky groups are away from each other. It's like this bulky group is down, this bulky group is up. And then we fill in our lines. Like that. You don't have, remember, once again, you don't have to do this. This is how I do it. You could go straight to with enough practice, go straight to the product. All right. So once again, start off by drawing your cyclohexene. If you wanted to, you could label carbons. I've seen students do this in the past. When I've suggested this, they do it also. So basically, the 1 and 4, I'm making little red dots, and then there are these right here. So that can help keep things in track. And then we have this branch here, and then this branch here. We are done. All right. Let's do another one. So next one here. So sometimes if your diene is already a ring, you get a bicyclo compound in your product. Bicyclo means two rings fused together. These can be difficult to draw for some students. I typically have students draw the flat drawing, and then if I have a question about the three-dimensional drawing of it, I typically will provide a picture, because they are difficult to draw for a lot of people. But I'm going to do my best to draw the product flat and in 3D for this one today. All right, so when you have all this extra stuff on the compounds, don't let that confuse you. The same principles are the same. You're going to have the 1 and 4 carbons connect to the alkene, and then you get a cyclohexene, tack on the other pieces. That's all there is to it, guys. So just remember, tack on the extra pieces. So start off with your cyclohexene, like that, and then tack on my pieces. And just like the last one, I'm going to go ahead and label the carbons with dots again, just so we can see what's what. So those 2 dots are going to be these 2 dots, and then tack on the rest. So coming off of this part here, we have this whole other ring. So that's over here. Like that. And then don't forget, between carbons 1 and 4, we had a ring there already. These 2 carbons are still there. So they're drawn as a bridge, like that. This is a bicyclo compound. So once again, if your diene is a ring, you get a bicyclo product. I guess technically this one's a tricyclo, right? Because we got 3 rings here. But yeah, let's go ahead and call it bicyclo. Or polycyclo. That could be a good word too, right? Polycyclo product. That way you encompass all of it. All right. So the reason why the 3-dimensional drawing works is because the way the ring actually attaches does make a difference. So I'm actually going to draw 3 dimensions, and we'll see if we can understand it all. I'm just going to go ahead and draw the major product and talk through it. Oops. Yeah, let's do it that way. All right, so we have that double bond here. All right, so what I have drawn so far is this portion of the molecule. So this part here where I have the double bond that kind of bends up like that, that's this part right here. So this little bridge here is this bridge. And I'm gonna just so we're all being clear, I'm gonna mark the same carbons that are marked here. I'm gonna mark down here. They're these ones. Oh, and as a little side note here, for those of you going on to 241, we go over the naming on these during the nomenclature chapter. These are kind of tricky to name, and we do that in that class. All right, so the part on these ones for the answers are what's happening with the other ring here. So whatever groups here that are attached from the Dienophile are going to be downward relative to the bridge. Once again, and then the H's are up. So there's your 3D drawing. So in a situation where if I had, like, on a test here, I'm thinking like a multiple choice question. If I gave you like both the endo and exo products, basically one down, one up products, you can predict which one's the correct one. So the one where the carbon piece is going down relative to the bridge is the major product. If you think about it, if you have this going up, these bridges are getting close in proximity. So steric strain wants to force it down, force it away from it. So you can think of it as, remember going over BS EPR, how molecules will kind of arrange to be as far apart from each other as possible. That's the same kind of concept happening on a larger scale. It's happening across the molecule rather than it being one carbon, for example. All right. The last one I want to go over here. Oops, so before I continue, I did want to point out two things on this thing here. So earlier when I was talking about nucleophile versus electrophile, it turns out the groups that are on there has an impact. So we're going to see this again next week when we do the aromatic stuff here, but I want to add it to the notes here. Electron donating groups make nucleophiles stronger and electrophiles weaker. You think about it, they're pushing more electrons into it. Nucleophiles are already characterized as being electron rich, so making them more electron rich makes them stronger, more reactive. EWGs do the exact opposite. These make electrophiles stronger, and they make nucleophiles weaker. So with that out of the way, looking at the problem that we had here, if you actually go back through the last two problems here, the nucleophile had donating groups on it, and then the withdrawing group had, the electrophile had withdrawing groups on it. And we're going to see that kind of throughout this chapter here. Yeah, so this is a donating group, a methyl group, and then withdrawing groups. Something to recognize. I didn't want to go over right now what all the different groups are. They are in the videos here, but you guys should have seen what the different groups are. Alkyl groups are donating groups. Carbonyl-carbons are withdrawing groups. All right. So I had one more Diels-Alder, and then I wanted to just crank through the aromatic first page of the aromaticity worksheet and then call it a lecture. All right. Maybe a little mouse pad. See, even the detail on my mouse pad is showing up now. So that's actually what I've been writing. Oh, today I'm writing on a mouse pad. I think I like it better than writing on the desk. A little softer. All right. Oh, where'd my problem go? Let me just set this here. All right, last problem. So this type of problem is where you are given the product and you are asked to go backwards and tell me what the diene and dienophile were. That, and then this one had this. So in these kind of problems, I noticed that these are a very common trick that some people will try to do. Notice here how I have a bicyclo. What this problem is trying to trick you to do is to think that your diene is a ring. It's not a ring. In order for you to get the ring, you have the cyclohexene with the bridge in it. That always happens. So if you don't see a bridge in here, that means that your diene was a straight chain. Oop, bumped the camera. Still in focus. Yeah. All right, so what I like to do here is same thing we were doing earlier, how I was highlighting new bonds. You can basically do the same thing here and kind of just break it there. So new bonds here are like that. Those were the new bonds. So then, and the correct arrow here, sorry about that. We haven't used this arrow in this class yet, but this is the Retrosynthesis Arrow. It means going backwards. So once again, this is called the Retrosynthesis Arrow, and it means going backwards. It looks like an equal sign with the big, making an arrow out of it. All right, so here was there's your basic diene structure. And then you had the OCH3s. I know these are going to be on this side of the compound because of the fact of the carbon it's on, is an obvious giveaway. Also, it makes sense for the donating groups to be on the nucleophile. All right, and then the rest of the molecule, boom. That's it. All right, looks like someone's typing a question. So the question was, with the cyclohexene needing a ring or needing a bridge. So let me pull up that earlier problem that we did today. Yeah, so it works out in these problems here. We have, if your diene is a ring, you get a bicyclo product, meaning you have the cyclohexene ring with the bridge inside of it, like that. We don't have that on this one. We did not have that on this one, so that's how I knew that this was not a ring. In order for this to be a ring, you have to have the carbons on the inside part right there. Does that make sense? Okay. All right. This next part here, we're going to switch gears a little bit. I think what I'm going to go ahead and do is just pull up the worksheet. I think my lighting is it too bright? I'm not sure. I'm still working on the lighting thing, but it looks like I'm washed out a little bit on my screen. But anyway, I'm pulling up the worksheet. We go ahead and work through this stuff here. Hang on. This one? This is the Then the camera needs to be changed. There we go. All right. So here is the first page of the aromaticity worksheet that's in Canvas. So this particular chapter, you got to do a couple things. The main part here I want you guys to be aware of is the concept of aromaticity. Let me actually switch to the face cam for this part. So essentially what aromaticity is you have a situation where electrons are able to freely flow around a ring. It turns out that is a very significant stabilizing feature in nature. If you actually look at a lot of biological compounds, a lot of them actually have these benzene rings incorporated into them because they are definitely a stabilizing feature. They're unreactive under most situations. We're going to see the next chapter. We can make them react under very harsh conditions, relatively harsh conditions actually. It all depends on what exactly you throw in there. Anyway, they are very common. So there are some criteria that must be met for this to work. So first off, the molecule must be planar. It also must have double bonds in conjugation, or a pi bond system in conjugation. So remember what that means from last chapter, that they alternate double, single, double. It turns out if they're double bonds right next to each other, they're actually perpendicular. They must be parallel. Parallel double bonds. Also, the last factor that comes into play is the number of electrons that are in rotation. We don't go over here. Some textbooks go over it, but it's actually a quantum mechanical explanation for this. It's a bonding versus anti-bonding, molecular orbital theory stuff. You guys probably started molecular orbital theory last semester in 122. But the short version is that if it does not have 4n plus 2, an integer amount, 4n plus 2 electrons, the compound is anti-aromatic. So let me go ahead and switch over to presenter real quick. So this is called a Huckel's rule, or Huckel. I think someone told me that the U with the dot over it is pronounced Hu with the U sound, oo sound. So Huckel. If anyone wants to let me know, his name is spelled with the 2 dots on top. I've heard it's pronounced Huckel. If anyone wants to knows better than me. All right, so people always attribute Huckel's rule as being 4n plus 2. I want to emphasize pi electrons or lone pairs in aromatic resonance. I'm going to show you a situation where we count the lone pair and one where we don't count the lone pair if there's heteroatoms. All right. So, taking a look here. All right. So it works out for all three. Like there's sets of 3 on this problem right here. I did the 7-membered ring. Yeah, 7-membered ring, the 5-membered ring, and the 3-membered ring. Basically, the more unusual ones. Benzene is too common. So of course, I didn't put benzene on there. It works out for all 3 of these. There's 1 aromatic, 1 non-aromatic, and 1 anti-aromatic. I believe. I know for the first set there is. So first things first, if you see a carbon in there that is a CH2, and that carbon would need to be part of this one right here is non-aromatic. Once again, non-aromatic. Going back to this here, so I want to make sure we have some numbers here. So if n is equal to 0, it's 2. So it's basically it's every other even number. So it goes 2, 6, 10, 14. We're not going past that, etc. Yeah. So the question was non-aromatic due to being non-planar. That is correct. Yeah, so an sp3 carbon is not planar, so that doesn't work. So you have to basically change it. Correct, they are typically sp2 hybridized. The exception to the hybridization is if they are a lone pair on us moving. Technically, the hybridization might be sp3, but for carbons, they're typically sp2. All right, so looking at this one here, these are both planar potentially. This one and this one. It works out though to get the full 360 resonance. This one has to push 6 electrons around. This one you have to include this lone pair to get a full 360. Oops. So this one has 6, this one has 8. Which one is aromatic? The left or right one? Is left or right aromatic? A little tick-tock timer there. Tick-tock, tick-tock. Yep, left is aromatic, right is anti-aromatic. So once again, to summarize, aromatic, keep doing that. Aromatic, non-aromatic due to being non-planar, and then anti-aromatic. So I think anti-aromatics are very interesting because anti-aromatic is a situation that's very unfavored in chemistry. So what happens here, if you have a compound that's planar that happens to be anti-aromatic, in nature it'll curl on itself. And why do you guys think why that molecule would naturally curl on itself? What does that do? Short version, it makes it non-planar anymore. So if it's non-planar and no longer satisfies the criteria for aromaticity, it's relieving the high energy situation. It works out where if you have a non-magic number and it's following all the other criteria for aromaticity, it's very high energy. So once again, to alleviate that, nature will curl the molecule to keep it from being aromatic, avoiding the situation. All right, next one. All right, so just follow your rules. Remember your magic numbers. So the question is why is the right one 8 pi electrons? Is because in order to get the full circle on resonance, you have to move 8 electrons. You have to include the lone pair. Yes, you have to include the lone pair if you did a full 360 of resonance on the structure. All right, next one here. This one is anti-aromatic. So this molecule is planar, but you're pushing 4 around. So to push those 4 around, that's non-magic number. All right, this one here is aromatic. Cyclopentadiene anion, definitely a well-known aromatic compound. Yeah, this is cyclopentadiene anion. Very, it's a common ligand used for metal chelation, but yeah, whatever. It's an aromatic compound. All right, next one here is also aromatic. This is actually furan. I want to go ahead and talk about this one on paper. So this compound is called furan, F-U-R-A-N. All right, so this one here, a common incorrect answer on this one I've seen students do is they will call this one anti-aromatic. This compound is aromatic. So I want to go ahead and do a resonance practice with this one, just to make sure we're getting our resonance practice. So the goal on showing whether a compound is aromatic or not is you got to think about what electrons are going to move in the resonance. So this one is aromatic, we'll see. Positive aromatic. So we have to do the 2 arrows at a time like that. Otherwise, we're going to violate octets. We're going to have a bunch of non-zero formal charges going on here. So we got a lone pair here. We have 2 bonds. Lone pair jumped over here. All right, oxygen is now plus, like that. You're essentially just going to keep, I think you have to push it around twice to get it to go back to your starting point. But I want to go ahead and do a couple more just to make, you guys can see how we're going with this. We're going to do this now. Yeah, some of these ones you have to actually go around the wing twice in order to get the full 360. But it does happen because that double bond is now over here. And then double bond here. Still plus. Get off your bum notification. All right, where were they at? We're still going. I think we're going to finish it. It's not them anymore. So, bam. So my goal here is to push it around to make it become like the starting one was. That way you know you got them all, right? So double bond is now here, double bond there, lone pair plus. So on every single structure, everything here is neutral, overall neutral. And I should have an arrow there, the resonance arrow up there. All right, and then one last one, double bond goes back, this lone pair goes back. And we are back to the start. And once again, I said that this compound was called furan. And while we're on this page, I'm going to mention that I showed you guys this earlier this semester. This one was THF. We called it tetrahydrofuran. The reason why it has that name is because if you compare them, this has 4 extra hydrogens, thus the tetrahydro. That's where the TH comes from in that name. So getting back to the problem at hand here, notice here how on every single one of these, that lone pair didn't move. You see that? It's still there, still there, still there, still there, still there. So when I'm doing the Huckel's number count, I don't include it. So one of the lone pair is not included. So the lone pair that did not move is not included. All right, not included in Huckel's rule. Huckel's rule. I think I'll say Huckel one time and Huckel the other time. So I'll say it both ways, make everybody happy. All right. Any questions about anything in general about aromaticity? All right. Another one I want to mention here is another one that's pretty important. It was important for me for a long time. Is thiophene. I like to call it the Superman molecule. You guys will not unsee it now. This is totally the Superman molecule. Superman. And this is called thiophene. Yep, exactly. Exactly. So the comment in the chat was it's aromatic, 6 electrons total. That's why it's aromatic. 100% correct. Yep. Good job. I want to mention this one here. This is also aromatic for the same reason that furan was. So one of the lone pairs won't move, one will. So this compound is aromatic. So the next examples I'm gonna draw here, these are all aromatic compounds that have heteroatoms in them. Perol, I think this one was called. So this compound is aromatic. I keep thinking it's perol. Sorry, I should have been more prepared today. Pyridine is also aromatic. So once again, all 3 of these are aromatic. So now the fun question, looking at these 2 compounds, and remember, think about aromaticity and whether or not that lone pair is part of the resonance for the aromaticity. The question now is, which is a stronger base? The left or right one? Which lone pair is more available for an acid-base reaction? Is essentially what the question is asking you. Yep, the right one is more basic. So the reason why is because that lone pair is not part of the aromaticity. This one is. So in order for that one to react with something, it's going to have to give up the aromaticity. Remember, nature favors the side that's more stable. The side that's aromatic versus the side that's non-aromatic is going to favor the aromatic side every time. So this side it's favored to be this way. This lone pair is not available for acid base. So this one here is a very weak base. Lone pair in resonance for aromaticity. This lone pair is free. free lone pair. Stronger base. All right. Another thing I wanted to mention here too, earlier this semester I did talk about how there are certain words in science that are that are technically incorrect, but they got so ingrained in the language we keep them in the language anyway. The word aromatic, in terms of the way we use it in chemistry, also is incorrect. So what people were finding back then, they were finding that compounds that had like this high degree of unsaturation tended to have strong aromas. So they thought that there was a characteristic in the molecule that made them have these really strong smells. Come to find out that it wasn't the case. It turns out that functionality plays a big part in that. Esters, for example, a lot of them have fruit smells. A lot of your fruits have esters in them, making them that smell. But it turns out that the term for aromaticity was a little bit different. So we found out it was definitely a stabilizing feature, essentially, not necessarily a factor of smell. Kekuli was the one that figured out the structure. Kekuli is actually the kind of drawing we're doing. They're called Kekuli structures. He's actually the gentleman who figured out that that benzene was a thing. And interestingly, what caused him to basically have a revelation on what benzene was the fact that he had a dream of a snake eating its own tail. Essentially, what happened. So what the problem was is they had a compound, benzene, that was a C6H6. If you do the IHD calculation for this, this is an IHD of 4. At this point, there was a lot of knowledge of the bromination reaction. So we covered the bromination reaction earlier this semester. Actually, last week? That reaction is used qualitatively in the lab as a test for unsaturation. Elemental bromine, I'm not sure if I mentioned this during when I lectured over it, but elemental bromine is a brownish orange color, and then the brominated alkane, the product is colorless. So color going away is a positive for this test, meaning there is unsaturation in it. If there is no unsaturation, the solution just stays orange. They were finding out they were getting negatives for this. Even though it had an IHD of 4, they kept getting negatives for the bromine test. So that stumped scientists for quite a while until the one day Kekuli had a dream about a snake eating its own tail. And I always tell my class too, if you have a snake eating its own tail, that means it's under very high stress and you need to take it to the vet. And it's probably due to being in captivity, unfortunately. From what I understand, there was one day where I looked up, like, why do snakes eat their own tail? And started looking into it. And what I was reading was that it's a stress coping mechanism, and not healthy for them at all. So yeah, so if you have a reptile eating itself, take it to the vet, please. They'll help you. All right, I think we had just a little bit left to do here. Let me go back to the browser. Yeah, just the last set here. So these are all two electrons, 4 electrons, and then 2 electrons. So this last one here is anti-aromatic. Which one's aromatic out of the 2, left or right? What do you guys think? Left or right is aromatic out of these 2? These 2 right here. Left is aromatic, correct. Left is aromatic. Right is anti-aromatic. So it goes aromatic, anti-aromatic, non-aromatic. All right. Awesome. For the exam, you can expect stuff like the acid-base question I asked. You can also expect, like, is it aromatic or not, kind of thing. All right. Last question here I want to take a look at. I do want to mention this one has a typo in it. This one should have had an H on it. So my bad. Drawing an H right here, guys. There should have been an H there. Because otherwise that becomes very obviously the most acidic H. Sorry, most basic N. All right. It works out where the least The least basic one is going to be the aromatic one. So this ring is aromatic. Ring is aromatic. That lone pair is not available. So automatically that is last. Dead last. It's going to work out where your No, there's the H coming off the N. This should have an H coming off of it. Yeah, the correct order should be for most to least. Most is going to be B, C, A. Is that what you wrote? Yeah, A should be last. A is aromatic, the aromatic lone pair. So once again, the order is B, C, then A. This is an amine. These are both amines, but this amine is aromatic. This is an amide. Amide are not basic due to resonance also. So this is all resonance, guys. You should not have very much you can do with this one. All right. I think we're at a good stopping point. What do you guys think? I think we are. So we're going to stop here. You guys have any questions about anything before I cut the stream today? You guys feel ready for that test? I hope. I hope everybody had a wonderful 4th of July. I know mine was pretty fun. We did fireworks right out there, front yard. So it was fun. No questions. All right. I'll go ahead and cut the stream here, guys. Remember, yeah, so I'm going to try my best to get the exam up tomorrow. For sure. Might not be early in the morning, but it'll be up tomorrow for sure. And then I'm still planning on streaming tomorrow also. I was going to work on some more like challenge type problems. We could do more review from the last week also. Think about what you guys want to work on and then make requests for what you wanted me to work on. Otherwise, I'm just going to work on the newest stuff. So, all right, guys. Stay safe, stay sane, and stay studying, right? Stay cool. All right, guys. I will see you guys tomorrow or talk on the Discord. All right. Goodbye.